Right, so now we're going to start section 7.3. In section 7.3, we are going to talk about our central limit theorem for sample proportions. So in the last section, we saw that as we changed or increased our sample size, the shape of our sampling distribution changed. Right, we said the big key thing, key sentence that we came up with, all of those different discussions based on our sampling distributions and our simulations. The larger the sample size, the more precise and normal the sampling distribution. So that's going to be something, again, that will be used in this section. In this section, we will explore the central limit theorem, which gives us a very good approximation of the sampling distribution without our needing to do simulations. So instead of having to look at a bunch of different simulations like we did in the last section, we're going to be able to find a way of approximating some things without doing that. So, as we're going through our central limit theorem problems, we're going to have three conditions that need to be met. So, condition 1, the sampling is random and independent. This has to be true in order to eliminate bias. So, in the last section, we did a lot of examples where we subtracted and we found the difference to show that there was no bias. In this case, if our sampling is random and independent, we're not necessarily going to show that that subtraction is 0. We're going to say that that's going to eliminate the bias. Our second condition is that we need a large sample. Our sample size, so n, is large enough to have at least 10 successes and 10 failures. And then what we see written next to that, n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. P is our probability of success, 1 minus p is our probability of failure, and if we multiply those by our sample size, we should get at least 10 for each of those. Right? And then our third condition is going to be that we have a large population. Right? N must be at least 10 times larger than our sample size. Right? If these three conditions are met, then our sampling distribution for p hat is a normal distribution. Remember, this n notation means a normal distribution. Our mean is going to be our p, our proportion for p, and then our standard error is going to be our standard deviation. Right? So this central limit theorem is going to be the basis of a lot of the problems that we're going to look at going forward. Right? So before we do that, we're going to kind of look at a couple of things, kind of the little pieces to these different problems using our simulations from the last section. So when we were going through our simulations in the last section, in simulation 2, we were told that our population size was 1,000 and our sample size was 10. So this time we consider a population of 1,000 people, 250 of whom are CAP people. We take random samples of size 10 and find our proportion. And then if we look at this and we think about our conditions of our central limit theorem, our central limit theorem says in order for a sample to be large enough, we need to be able to multiply n times p and n times 1 minus p and get values that are greater than or equal to 10. If we take n times p, in this case, we take 10 times 0.25, well, we only get 2.5, right? Which is not big enough. So in this case, we would say, therefore, the sample size is too small. And we cannot use the central limit theorem, the CLT. Okay. So one thing that we will be looking for and we will be checking is we're going to be doing a quick multiplication to make sure our sample size is large enough. Right, if we look at one of our other simulations from the previous section, this time we consider a population of 1,000 people, 250 of whom are CAP people, so we still had a population proportion of 25%. This time we increased our sample size from size 10 to 100. In this case, if we go through and we check all of our conditions of our central limit theorem, they will all work out. That multiplication that did not work last time would work this time. So since all of our conditions of our central limit theorem are satisfied, we are allowed to find our standard error. Right? So we're going to plug in 0.25, because that's our p, times 1 minus 0.25. Right? So we always take p times our complement divided by our sample size, which is 100. So we're taking 0.25 times 0.75. We're dividing that by 100, and then we're taking the square root of that. That is going to give us 0.0433. Again, the less rounding we can do until the end, the better. So you want to practice getting these into your calculator and getting as you're plugging them into your calculator, you should be getting the same answers that I am getting. Right? So our sampling distribution is a normal distribution that has a mean of 0.25, because that was our population proportion, and a standard error, I'm going to round this to 3 decimal places, of 0.043. Right, so our central limit theorem says certain conditions need to be met, and as long as those conditions are met, then we have something that is close to a normal distribution. Right, and what we're going to do from here is we're going to use this normal distribution to answer some questions. And that's what we're going to look at in the next video, and then the rest of the examples for section 7.3.